At this point, we've covered electric charge, electric fields, Gauss's law to determine electric fields with basic charge configurations. And now we are ready to enter into a study of electric potential, which is perhaps the last part of our theoretical understanding of introductory electricity. Well, let me start by just cutting to the chase and defining what we mean by electric potential. So, as a definition, it is energy per charge, simply that ratio. Now, energy is obviously related to work, so we can call it work divided by charge as well. Or, a little more precisely and to the point, it's the negative change in potential energy divided by the charge. And what's that? That's called the negative change in voltage. So that's what we have, with the unit being the volt, and that's a joule per coulomb. Keeping in mind that potential, even though it relates to vectors, potential itself is a scalar quantity.
Wait a minute here. Volts, joules per coulomb, work per charge, energy per charge, voltage. What is all this stuff? We better take a big step back and sort it all out here before we just go crazy.
Indeed, we don't want to end up in a psych ward over these ideas, so let's start with the basics. And the basics are defining work. Work moving an object from A to B. In general, that's integral of F dot dl, as we have come to know. And a dot product is F cosine of theta dl. And so we're going to relate this to our ideas of charges here. But this quantity is negative change in potential. This is true for a conservative force, and it turns out that electric fields produce a conservative force on charges. So this will be very applicable. We have then F cosine of theta dl. This whole thing is what we call a line integral. So moving an object, in this case a charge, from A to B, if there's a force on the charge, which means there's an electric field, this is the work done by that electric field in moving the charge over this integral, over this path, I should say. So we integrate dl over this entire region, multiplied by the particular force across every point. Let's consider conservative forces, because that's what we're dealing with here. But let's do the gravitational analog, since we're probably more familiar with that. So we have a region here with a G field, and we're going from A to B along some arbitrary path, as shown here. And the work done by the conservative force in moving the object from A to B. So we're interested in the work done by gravity along this path. So the work done by the G field moving from A to B is independent of the force that caused it to move in this path. So you, as an external agent, perhaps are grabbing this mass and moving it along this path. Doesn't matter how fast you do it. Doesn't matter what shape the path is and what transitions occur. Makes no difference as far as the work done by the gravitational field. It's the nature of a conservative force field. So that work is positive in this case because G is essentially moving or acting downward. It's putting a downward force. So we go from A to B. There's a net quantity of work done by that G field that's positive. And that's the potential energy at A minus the potential at B, which is the negative change in potential energy. Change is B minus A. So UG has gone down in the process. We start with a higher potential, go to a lower potential. The potential has gone down. Now if we reverse these roles, G field the same, but in this case we got A on the bottom and B on the top. Maybe the path has changed, it doesn't matter. Now the work done by the conservative force field, the gravitational field, on the object and moving along this path is negative. UA minus UB again, negative change potential energy. The potential energy has gone up. So we'll take this same idea and relate it to the work done by an electric force field on a charge. As we consider an electric charge in an electric field, we'll notice the tight correspondence with the gravitational analogy. So we have an E field. We're going to put a plus charge Q0 between these charge distributions, which could be just sheets of charge, plus and minus here. Notice this electric field is really distributed across the whole thing. I just don't want to show the field lines because it'll clutter up the diagram. Well, the electric field puts a force in the direction of positive to negative. So in the direction of the electric field, it's the direction of force on a positive charge, and it's given by charge times electric field. That's the force. So here's the path that we're going to allow the charge to move along. Since it's a conservative force field, work by that field, moving the charge from A to B is negative delta U. Particularly, work A to B is force times charge. Q0E, force times D. D is the distance from one sheet to the other. So that's the work done by the E field. It's positive in this case. It's shoving. The E field is shoving that charge from A to B. The potential energy in a uniform force field, then, in summary, for gravitational, we have gravitational potential energy mgy. This is a uniform field. This is the assumption that the potential energy is 0 at location B. The force in the y direction is negative mg because g is acting in the negative y, or down. Likewise for electrical, U sub E, Q0E, y. The force in the y direction is minus Q0E, where E field is down, or from A to B. So you see how tight that analogy is. Now let's consider the motion of charges in an electric field and the corresponding change in potential energy. So we have an electric field, plus and minus charge. The force in the plus charge is in the direction of the E field, but let's have it moving in the opposite direction. Likewise for the negative charge, the force is in the opposite direction, but it's moving in the opposite direction of that force. So in both cases, the motion is directed opposite to the force, and that results in the potential energy going up. In the same way, electric field, let's have the force on the plus charge in the same direction as the motion. Same with the negative. Everything is opposite here, but the motion is in the direction of the force in both cases. If that's true, potential energy is going to go down in both cases. So this is a little bit different than just gravity, because gravity, the force is always toward the mass. The gravitational field is always toward the mass. So that's the direction of force on a mass in a gravitational field. So we don't have these opposite concerns here. But if the test charge moves opposite the electric force, which could be either direction depending on the sign of the charge, the electric potential energy goes up, and if it moves in the same direction as the force, the electric potential energy goes down.